Okay, so what's the idea here? Well, we asked you to drag the boxes in the order in which they appear here. And the whole idea is that later in the week you're going to learn that from the post condition and the precondition, which are already here for this drag and drop, you're going to systematically come up with the loop invariant, and then in week 2 you learned where the loop invariant needs to be true. So this is going to be the loop invariant, and that loop invariant is going to be true before the loop starts. That's your base case in your mathematical induction. At the top of the loop body, that is your inductive hypothesis. You will then develop the loop so that it's again true at the bottom of the loop. That is your inductive step. And then if you ever come out of the loop, it's going to be true after the loop finishes. Okay? Now the next thing you learned in week 2 is that the loop invariant together with the loop guard being false should imply that you've computed the correct thing. Now, how should you pick your k in order for the loop invariant to imply the post condition? Well, your k should be equal to 0, and notice that if you pick your loop guard to be 0 is less than k, then not 0 less than k, then k is less than or equal to 0. And if k is less than or equal to 0 and 0 is less than or equal to k, you know that k is equal to 0. So that becomes your loop guard. So notice that we have systematically reasoned through what the loop guard must be. You might have been tempted to pick up k less than n because you would have assumed that you're marching through the loop from 0 to n, but you should have noticed that actually we're decrementing k every time through the loop. So you place that everywhere where the loop guard should be true. Let's see, the loop guard right there. Okay, so then you notice that all of these have to do with guards, and we're going to skip them because they would have been incorrect. So the next question you ask is, well, how should you initialize k? Well, notice that initially you would like S to be the summation over no elements in B at all. And what does that mean? That means that k should be equal to n, because then you do the sum over the empty range, and that means that you're not summing anything. So the correct initialization here is k is equal to n. And then finally you notice that if you take your k equal to n, then you're doing the sum over the empty range, so then s must be equal to 0. So if we pick our s equal to 0, then we end up in a state where the loop invariant is true. So we drag that in. And then you're done. But the important thing is that this is goal-oriented reasoning. We started with the precondition and the postcondition, and we reasoned through what the states of the variables should be at various points, and that allowed us to then figure out what's going on. Oops, we've forgotten one thing, and that is the upstate step. And here you actually have to think through kind of carefully. And if you think through carefully, and we're going to teach you how to think through very carefully later in the course, you're going to conclude that S should be S plus B of k. And there you have it. This is a preview of what you will see in section 3.5 this week.